In this video, we are going to learn about the sampling distribution of the sample proportion. And I'm going to be using this DCMP app to do a simulation of this scenario. So before we get into this, let's think about an example. So 23% of Americans have found to smoke. So that means our population proportion would be 0.23. Which means out of every 100 Americans, 23 of them would smoke. Now, suppose we take a sample of 30 people and we find that 8 of them smoke. So this would be 8 out of the 30 people would smoke, which would mean our sample proportion would be 0.27. 0.27 is obviously not the same as 0.23. So does this mean our population proportion is wrong? No, it does not mean that, because in order to get a sense of the pattern of variation in sample proportions, we need to generate multiple samples. We can't just use one, because each sample is going to be different. So that means we have to take multiple samples, and the distribution showing how the sample proportions vary from sample to sample is called a sample distribution of the sample proportion. So let's go ahead and try this out and see what this looks like. So what we're going to do is we are going to have our population proportion here, the 0.23, and we're going to take a sample of 30 people. So let's take a sample of 30 people, and you can see that we found 9 out of the 21 people in that sample said that they smoked. So we got a sample proportion of 0.3, which is different than our population proportion of 0.23. And it's different than the one that we talked about earlier. So let's go ahead and take another one and see if that's the same. Now this one, we end up with 0.13. Again, we get a different sample. Each of these samples are going to be different due to the different group of people that we are polling. So I'm going to keep drawing these. And see, this time we got 0.23, now we got 0.13, now we have 0.17. So I'm going to keep going until we get a good amount of these. And as we keep going, you can see that our mean is changing. And the more and more we do, the closer that mean is getting to the actual population proportion. So you can see we have a pretty good amount here now. And now that we have all of our proportions, we can see about 3 of them got a sample proportion of 0.1. We had 6 of them get a sample proportion of 0.3, and so on. So you can see that the mean, if we take the average of all of these sample proportions, so we take the 0.1 plus the 0.1 plus the 0.13 plus the 0.13 and so on, take them all, add them all together, divide by however many they are to get the average of all those sample proportions, we end up with an average of 0.23. And we end up, if we take the standard deviation of all of these different sample proportions, we end up with a standard deviation of 0.0749. So you can see that the average of all of our sample proportions is the same as our population proportion. And this standard deviation of all of the sample proportions is going to end up being our standard error. Now, instead of doing this by simulation, we can use the definition. So let's go back into our notes here. And we can see that rather than using simulation, we can use a mathematical theory to derive expressions for the mean and the standard deviation of the sampling distribution of the sample proportion. So the mean of the distribution is the same as the sample proportion P, which we found was at 0.23. And the standard deviation of the distribution of the sample proportion is the square root of P times 1 minus P over n. So let's try that out. If we take the square root of p, which we said was 0.23, times 1 minus 0.23 over our sample size n, which we said was 30, n equals 30. And let's go ahead and do that in our calculator. And then when we put that into our calculator, let's see what we end up with. So I'll give you a chance to go ahead and do that. And you should end up with something very similar to what we have for the standard deviation. So what I ended up with, 0.0768, which is very close to that 0.07 we had in our simulation. So you can see the simulation is not going to be 100% the same as our theoretical version unless you take a whole bunch more samples. So let's say we take 1,000 and draw the samples, and we'll end up with 0.075. And you can see as you keep taking them, it's going to get closer and closer to what we found before. So you can see we end up getting 0.076 here, which is the same as we found 0.076 in our theoretical version. So that is how sampling distributions work for the sample proportion.